We often imagine the universe as infinite and unknowable. But at the smallest level, everything is built from a finite and elegant set of parts that fit onto a single table. The periodic table is one of the most quietly powerful tools in all of science. To someone unfamiliar, it may appear as a simple grid of symbols and numbers, but this arrangement is more than a chart. It is a deep structural map of the natural world. It brings order to chaos, organizing all known chemical elements into a coherent framework based on repeating patterns and predictable behaviors. With a glance, it tells us not just what an element is, but how it behaves, who it bonds with, and even where it came from in the story of the universe. For scientists and learners alike, the periodic table offers not just information, but insight, a way of understanding the relationships between the building blocks of matter. Each element on the table represents a different type of atom, distinguished by the number of protons in its nucleus. This number, known as the atomic number, increases from left to right and from top to bottom. Hydrogen, with just one proton, is the first. Uranium, with 92, appears far down the list, and beyond it, elements too unstable to be found in nature have been created in laboratories. Despite their differences, all elements follow the same principles of atomic structure. This allows the periodic table to reveal trends in reactivity, size, and behavior that repeat in meaningful and useful ways. The table is organized into rows called periods and columns called groups or families. These divisions are not arbitrary. Elements in the same group often behave in similar ways because they share the same number of electrons in their outer shell. These outer electrons, known as valence electrons, are responsible for the chemical interactions that take place. Sodium and potassium, for example, are both in group 1. They each have a single valence electron and are highly reactive, especially with water. Their shared behavior is not coincidence, it's structural. Understanding the periodic table is not only for chemists. It helps explain why metals shine, why water molecules are bent, why certain materials conduct electricity, and why life relies on elements like carbon, nitrogen, and oxygen. The table connects the stars to the cells in your body, reminding us that everything from galaxies to grains of salt is built from the same small family of atomic parts. And somehow, it all fits neatly on this one quiet chart. Now we see how the table is organized as periods and groups. The structure that gives this scientific chart its extraordinary power and clarity. Although the periodic table contains more than 100 different elements, it is not a random list. Its true strength lies in how it arranges those elements into rows and columns that reflect deep, meaningful patterns. Each element is placed precisely based on 2 criteria: its atomic number and its electron configuration. The result is a layout where neighboring elements are not just physically close, but chemically related. It is this organization that allows scientists to predict how an unfamiliar element might behave, even before they test it. The horizontal rows on the periodic table are called periods. There are 7 in total, each one representing a new electron shell being added to the atom. As you move from left to right across a period, each element gains 1 proton and 1 electron. This gradual increase changes the behavior of the atoms in subtle but consistent ways. Atomic size, for instance, tends to shrink across a period because the increasing number of protons pulls electrons in more tightly. Electronegativity, or the desire of an atom to attract electrons, generally increases. These trends help us understand not only the properties of elements, but also why some bond readily while others resist. The vertical columns are called groups, or sometimes families, and there are 18 of them. Each group contains elements with the same number of electrons in their outermost shell. And this is where chemical behavior becomes most predictable. For example, group 1 elements, known as the alkali metals, all have one valence electron. This makes them highly reactive, especially with water. Group 17, the halogens, have 7 valence electrons and are known for their powerful reactions with metals. Group 18, the noble gases, have full outer shells, which makes them extremely stable and unreactive. These patterns are not coincidental. They reflect the deep relationship between an atom's structure and its behavior, while periods reflect the gradual buildup of atomic mass and structure. Groups reflect chemistry, how elements interact, form compounds, or remain inert. This dual structure, where rows and columns each tell their own story, allows the periodic table to do more than classify. It becomes a guide, a predictive tool, and a reference all in one. Even new or synthetic elements, once placed into the correct group, often behave as expected because of the patterns established by their neighbors. The periodic table, in this light, is not just a chart. It is a framework for understanding matter itself, a structure whose logic flows through every molecule, every compound, and every living thing. Now we begin to understand why atomic number sits at the center of the periodic table's logic. It is the number that defines what each element truly is. Every atom contains a nucleus made of protons and neutrons, surrounded by electrons that orbit in defined shells. Of these components, the number of protons, the atomic number, is what gives an element its identity. It is not mass, not name, not color or state. It is that simple count of positive charges in the nucleus that determines whether an atom is hydrogen, helium, carbon, or gold. Change the atomic number, and you change the element itself. A hydrogen atom with 1 proton becomes helium if it gains just 1 more. This number is the organizing principle of the entire periodic table. The table begins with hydrogen, atomic number 1, the lightest and most abundant element in the universe. It proceeds step by step, increasing by 1 proton at a time, forming a predictable ladder of structure and behavior. Each step brings a new element with its own unique properties, but these changes are not chaotic. They follow patterns that emerge because of the rules set by atomic number. As protons are added to the nucleus, electrons are added as well. These electrons arrange themselves into shells around the nucleus, and their arrangement determines how the atom behaves. This is why atomic number is more than just a label. It dictates how many electrons an atom has, and more importantly, where those electrons reside. An atom's chemical behavior, whether it bonds, how it bonds, what it bonds with, depends entirely on the distribution of its electrons. And that distribution is set by the atomic number. For example, oxygen, with atomic number 8, has 8 electrons arranged in 2 shells. The outer shell contains 6, meaning it needs 2 more to feel complete. This drives oxygen's tendency to form bonds with other atoms, often by gaining or sharing electrons. When an element gains or loses protons, it becomes a different element. This is different from gaining or losing electrons, which turns an atom into an ion. It is also different from adding neutrons, which simply creates an isotope of the same element. Only the number of protons, and therefore the atomic number, determines elemental identity. This principle is what allows us to place each element in its precise spot on the table, and it is what makes the table's structure so dependable. The atomic number is the simplest possible way to define an atom, but it is also the most powerful. It explains why helium does not react, why chlorine is hungry for electrons, and why gold stays gold, no matter how much it is refined. It is the silent rule behind the chemistry of everything. Now we turn our attention to the three fundamental particles that make up every atom: protons, neutrons, and electrons. Though impossibly small, these particles carry the structure and character of all matter. At the center of every atom is its nucleus, a dense, compact core made of protons and neutrons. Protons carry a positive electrical charge, while neutrons are electrically neutral. The number of protons in the nucleus determines the atom's identity and gives it an atomic number. This number tells us what element we are dealing with. For example, if there is 1 proton, it is hydrogen. If there are 6, it is carbon. This identity is unchanging because the proton count is the defining characteristic of each element. Neutrons add mass to the atom but do not affect its charge. Their role is more subtle. They act as a buffer between the positively charged protons. Without neutrons, the mutual repulsion of the protons would tear the nucleus apart. The number of neutrons can vary within atoms of the same element. When this happens, we call these variations isotopes. Some isotopes are stable, while others are radioactive, slowly breaking down over time and releasing energy in the process. This variation allows atoms of the same element to behave nearly identically in chemical reactions, even while having slightly different masses. Surrounding the nucleus is the cloud of electrons. These are tiny, negatively charged particles that move rapidly around the nucleus in energy levels or shells. The number of electrons in a neutral atom is equal to the number of protons, keeping the electrical balance. Electrons are not located in fixed paths. Instead, they are described by probabilities existing in regions called orbitals. These orbitals define where an electron is most likely to be found at any given moment. Electrons are responsible for almost all chemical reactions. When atoms interact, it is the outermost electrons that are gained, lost, or shared. This is what forms bonds and builds molecules. The arrangement of these electrons, how many layers there are, and how full the outer shell is, determines an element's reactivity. Elements with nearly full or nearly empty outer shells are often the most reactive. Those with complete outer shells, like the noble gases, tend to be inert and stable. While protons define the element and neutrons contribute to its mass and stability, electrons determine its behavior. The dance between these three particles is what makes the diversity of matter possible. Together, they form structures that are invisible to the eye, yet present in everything in the air you breathe, the cells you carry, and the stars above. Understanding them is a quiet step toward understanding how all of nature is constructed. Now we explore how electrons are arranged around the nucleus, forming shells and energy levels that define how atoms interact with one another. Electrons do not orbit the nucleus in simple circles, like planets around the sun. Instead, they occupy defined energy levels, often referred to as shells, which surround the nucleus at increasing distances. These shells are not physical paths, but rather regions where an electron is most likely to be found. Each shell can hold only a certain number of electrons, and the arrangement of electrons across these levels plays a major role in how atoms behave. The first shell, closest to the nucleus, can hold a maximum of 2 electrons. The second shell can hold up to 8. The third shell also holds 8, though it can expand in larger atoms. As electrons fill these levels, they follow a pattern based on increasing energy. Electrons fill the lowest available energy levels first before moving outward. This organization is known as the off-bow principle. It helps explain the structure of the periodic table and why elements in the same group share similar chemical properties. The outermost shell of an atom, often called the valence shell, is especially important. It is here that bonding takes place. Atoms strive for stability, which often means having a full outer shell. For hydrogen and helium, this means 2 electrons. For most other elements, 8 electrons in the outer shell is considered stable. This tendency to achieve a full outer shell drives atoms to form chemical bonds by gaining, losing, or sharing electrons. Different orbitals exist within each shell. These are known as s, p, d, and f orbitals, and each has a unique shape and electron capacity. The s orbital can hold 2 electrons. The p orbital can hold 6. The d orbital holds 10, and the f orbital holds 14. As atoms grow larger, these orbitals begin to overlap in more complex ways, but the fundamental pattern of filling lower energy levels first continues to guide electron arrangement. This electron configuration explains why elements behave the way they do. For example, sodium has 11 electrons. To go into the first shell, 8 into the second, and the last one enters the third. That lone electron in its outer shell makes sodium highly reactive, eager to lose that electron and return to a more stable configuration. Chlorine, on the other hand, has 7 electrons in its outer shell and is eager to gain one. When these 2 elements meet, sodium donates its electron to chlorine, creating a stable ionic bond. Electron shells and energy levels are more than just theoretical structures. They are the invisible architecture of atoms, quietly determining the properties of elements and the ways in which matter connects. In understanding them, we begin to see the logic behind the periodic table and the rules that govern the chemistry of the universe. Now we look more closely at the electrons in the outermost shell of an atom, known as valence electrons. These are the key players in chemical bonding and reactivity. Every atom has electrons arranged in shells or energy levels, and while all electrons influence the atom's overall structure, it is the electrons in the outermost shell that determine how the atom interacts with others. These outer electrons, called valence electrons, are responsible for forming chemical bonds, whether by being shared, gained, or lost. Their behavior explains why some elements react quickly and others remain stable and unreactive. The number of valence electrons in an atom can be determined by its position in the periodic table. For the main group elements, those in groups 1, 2, and 13 through 18, the group number gives a reliable clue. Group 1 elements, like lithium and sodium, have 1 valence electron. Group 17 elements, such as chlorine and fluorine, have 7. Group 18 elements, the noble gases, have full outer shells, which is why they rarely form bonds with other elements. Atoms seek stability, and in most cases, this means having a full outer shell. For hydrogen and helium, a full shell means 2 electrons. For most other elements, 8 electrons in the outer shell brings stability. This is often referred to as the octet rule. Atoms with fewer than 8 valence electrons will tend to react in ways that allow them to reach this more stable configuration. They may lose electrons, as metals often do, or gain them, like many non-metals. In some cases, atoms share electrons to complete their shells, resulting in covalent bonds. Consider sodium and chlorine. Sodium has 1 valence electron. Chlorine has 7. When sodium transfers its single valence electron to chlorine, both achieve full outer shells. Sodium becomes a positively charged ion. Chlorine becomes a negatively charged ion. The attraction between these opposite charges forms an ionic bond. This simple exchange is what gives table salt its structure. In covalent bonding, electrons are not transferred but shared. In a water molecule, for example, each hydrogen atom shares an electron with oxygen. Oxygen ends up with 8 valence electrons, and each hydrogen has 2. The result is a stable molecule where the atoms remain linked through mutual sharing. Valence electrons also determine properties like conductivity, hardness, and melting point. Metals with free-moving valence electrons conduct electricity well. Non-metals with more tightly held valence electrons do not. These traits all stem from how those outer electrons behave. Understanding valence electrons brings clarity to the periodic table. It explains the structure of molecules, the formation of compounds, and the regular patterns seen in chemical reactions. Though invisible to the eye, these electrons quietly govern the way matter builds, breaks, and bonds. Now we examine the periodic trends that emerge across the table, helping us predict how atoms will behave based on their position. These trends include atomic radius, ionization energy, and Although the periodic table appears static, its structure is full of movement, not physical but behavioral. As you move across a period or down a group, predictable patterns begin to form. These trends are not coincidental. They arise from the way atomic structure changes with increasing proton and electron count. They allow scientists to make informed assumptions about reactivity, bonding, and chemical properties, even before interacting with the elements themselves. Atomic radius refers to the distance from the center of an atom's nucleus to the outermost electron shell. As you move from left to right across a period, atomic radius decreases. This is because each successive element has one more proton in its nucleus and one more electron in its shell. The increased positive charge pulls the electrons in more tightly, making the atom slightly smaller. On the other hand, as you move down a group, atomic radius increases. Each step down, the group adds another electron shell, pushing the outermost electrons farther from the nucleus. Even though the number of protons increases too, the shielding effect of the inner electrons reduces the pull on the outer ones. Ionization energy is the amount of energy required to remove an electron from a neutral atom. This value tells us how tightly an atom holds onto its electrons. Across a period from left to right, ionization energy increases. Atoms become smaller and hold their electrons more closely. Removing one requires more energy. Down a group, ionization energy decreases. The outer electrons are farther from the nucleus and are more easily removed. This is why elements like cesium or potassium found near the bottom of group 1 are highly reactive. Their electrons are loosely held and easily given away. Electronegativity is the ability of an atom to attract electrons toward itself when forming a bond. It reflects how strongly an atom pulls on shared electrons. This trend increases from left to right across a period and decreases down a group. Fluorine, located in the top right corner of the table, is the most electronegative element. It strongly attracts electrons, making it highly reactive. Elements on the left, like lithium or sodium, have low electronegativity and tend to lose electrons instead. These three trends, atomic radius, ionization energy, and electronegativity, are closely connected. Together they explain why elements react the way they do and how the structure of the table mirrors their chemical behavior. They reveal a quiet logic, a gradual shift in energy and size that repeats again and again across the periodic table. Understanding these patterns deepens our ability to see the elements not as isolated blocks but as participants in a larger, orderly system. Now we explore the broad classification of elements as metals, nonmetals, and metalloids. categories that reflect distinct physical and chemical behaviors across the periodic table. Although each element is unique, the periodic table naturally divides into larger families based on shared characteristics. One of the most useful and observable divisions is between metals, nonmetals, and the elements that lie between them, the metalloids. This classification is not decorative. It is rooted in measurable differences such as conductivity, malleability, luster, and how atoms bond and share electrons. Metals make up the majority of the periodic table. Found primarily on the left and center, they include familiar elements like iron, copper, aluminum, and gold. These elements tend to lose electrons easily, forming positive ions. They are generally solid at room temperature, with the exception of mercury, and they are known for being good conductors of heat and electricity. Metals are often malleable, meaning they can be hammered into sheets, and ductile, meaning they can be drawn into wires. Their shiny, reflective surfaces are a result of how their electrons move freely, allowing energy to be absorbed and emitted easily. Nonmetals occupy the upper right portion of the periodic table. This group includes oxygen, nitrogen, sulfur, chlorine, and all the noble gases. Nonmetals differ significantly from metals in both physical form and chemical behavior. They tend to gain electrons during chemical reactions, forming negative ions or sharing electrons in covalent bonds. Most nonmetals are poor conductors of electricity. Many exist as gases at room temperature, while others are brittle solids. They do not have the same shiny appearance as metals, and their structures are more varied. Chemically, they are often more reactive with metals and can form a wide range of compounds essential for life and industry. Between the metals and nonmetals lies a narrow staircase of elements called metalloids. These include elements like boron, silicon, arsenic, and tellurium. Metalloids display properties of both metals and nonmetals. They may conduct electricity, but not as efficiently as metals, which makes them useful in semiconductor technology. Their chemical behavior can shift depending on what they react with. In some settings, they behave like metals, while in others, they resemble nonmetals. This duality makes them versatile and important in fields such as electronics, glassmaking, and material science. This classification, metals, nonmetals, and metalloids, helps us interpret the periodic table not just as a chart of atomic numbers, but as a guide to behavior. It provides a visual and conceptual framework for predicting how elements will interact, what kinds of bonds they will form, and what physical properties they might exhibit. Though simplified, this division remains essential for understanding the chemical landscape and how matter behaves. Now we turn to Group 1 of the periodic table, known as the alkali metals. These are some of the most reactive elements in all of chemistry, known for their simplicity in structure and their intensity in behavior. Group 1 includes lithium, sodium, potassium, rubidium, cesium, and francium. All of them share one defining feature: a single valence electron. This lone outer electron makes them both predictable and energetic. Because they have only one electron in their outer shell, these elements are eager to lose it, becoming positively charged ions with a full inner shell underneath. This eagerness to give up an electron is what makes alkali metals highly reactive, especially with water. Their reactivity increases as you move down the group. Lithium, the lightest, reacts steadily. Sodium, which is more familiar in everyday life as part of table salt, reacts more quickly. Potassium can ignite when it contacts water. And the heavier members, like rubidium and cesium, react so violently that they must be stored under oil to prevent contact with air or moisture. Francium, the heaviest in the group, is so unstable and radioactive that it is rarely studied directly. The physical properties of alkali metals also reflect their simplicity. They are soft enough to be cut with a knife, have relatively low melting points compared to most metals, and are excellent conductors of electricity. Their metallic luster is quickly lost when exposed to air, as they oxidize rapidly. When they do react, the results are energetic and visible. In water, they produce hydrogen, gas, and a strong base, usually a hydroxide, along with heat. This reaction is the basis of the term alkali, referring to the basic or alkaline solutions they form. Chemically, alkali metals form ionic bonds with nonmetals, especially with halogens from group 17. Sodium chloride, or table salt, is a classic example. In this compound, sodium donates its single electron to chlorine, forming a stable crystalline structure made of charged ions. This pattern of forming one-to-one ionic compounds is consistent across the group. In biological systems, certain alkali metals are essential. Sodium and potassium play critical roles in nerve function and fluid balance. Their movement across cell membranes generates electrical signals that allow muscles to contract and the heart to beat. Despite their high reactivity in pure form, in compound form they are safe, stable, and crucial to life. Group 1 demonstrates how a simple structure, just one electron in the outer shell, can lead to some of the most dynamic behaviors on the periodic table. These elements are a reminder that sometimes the most reactive systems come from the most straightforward foundations. Now we move to Group 2 of the periodic table, the alkaline earth metals. These elements are known for being slightly less reactive than their neighbors in Group 1, but they still play a vital role in both chemistry and life. Group 2 includes beryllium, magnesium, calcium, strontium, barium, and radium. Each of these elements has 2 electrons in its outermost shell. This pair of valence electrons makes them more stable than the alkali metals, which only have 1. However, they are still quite reactive, especially with non-metals. Like the alkali metals, they tend to lose their outer electrons easily, forming positive ions. But because they must lose 2 electrons instead of 1, it requires more energy, and their reactions proceed more slowly. The term alkaline earth refers to 2 key features. Alkaline comes from the basic solutions these elements form when they react with water or oxygen. Earth was an older term used by early chemists to describe substances that were stable, solid, and unaffected by heat. While we now understand their structure in much more detail, the name remains. The reactivity of alkaline earth metals increases as you move down the group. Beryllium, at the top, is relatively inert and toxic in pure form. Magnesium reacts gently with acids and is commonly found in nature. Calcium reacts more actively, especially when exposed to moisture in the air. Strontium and barium display even more pronounced reactivity, often producing colorful flames. Radium, at the bottom of the group, is radioactive and rare, with limited direct use due to its instability. These metals are shiny and silvery white in appearance. They are harder than Group 1 metals, with higher melting and boiling points, though still softer than many transition metals. Their physical strength makes them useful in structural applications, and their chemical behavior makes them common in earth minerals and biological processes. Magnesium and calcium are especially important in biology. Magnesium is found in chlorophyll, the pigment that allows plants to capture sunlight. It also acts as a cofactor in many enzyme reactions in the human body. Calcium is well known for its role in bones and teeth, but it also plays a key part in muscle contraction, nerve transmission, and blood clotting. The human body stores most of its calcium in the skeleton, releasing it as needed to maintain proper function. Alkaline earth metals also contribute to industrial chemistry. Calcium compounds are used in cement and plaster. Magnesium alloys are valued for their strength-to-weight ratio. Strontium salts are used in fireworks to create red flames, and barium compounds are found in medical imaging. Group 2 elements show how a simple shift from 1 to 2 valence electrons can lead to a wide range of properties, from gentle structural stability to dramatic flame reactions. Their chemistry is balanced, steady, and essential to both the Earth and the life it supports. Now we explore Group 13 of the periodic table, known as the boron group. This family of elements marks a subtle but meaningful shift in the periodic structure, blending non-metallic traits at the top with increasingly metallic behavior below. Group 13 includes boron, aluminum, gallium, indium, thallium, and the synthetic element nihonium. What unites them is the presence of 3 electrons in their outermost shell. These 3 valence electrons give the group its common chemical tendencies, but the way those tendencies express themselves varies widely depending on the element. As we move down the group, we see a gradual transition from non-metal to metal, from hard and brittle to soft and malleable. Boron, the first in the group, stands apart. It is a metalloid, meaning it shares properties with both metals and non-metals. It is hard, brittle, and poor at conducting electricity. In nature, boron is found in compounds like borates and boric acid. It plays a role in glass manufacturing, detergents, and even plant growth, although its full role in biology is still being studied. Boron's structure allows for complex bonding and unusual molecular shapes, making it valuable in materials science. Aluminum, the next element in the group, is the most widely used of them all. It is a true metal, lightweight, corrosion-resistant, and highly conductive. Found abundantly in the Earth's crust, aluminum is used in packaging, transportation, construction, and electronics. Though reactive in theory, it forms a thin oxide layer on its surface that protects it from further corrosion. This protective coating is part of what makes aluminum so useful and durable in real-world conditions. Gallium, indium, and thallium continue the trend of metallic character. Gallium is notable for its low melting point. It can melt in your hand, yet it remains solid at room temperature. It is used in semiconductors and LED technologies. Indium is soft and shiny, often used in touch screens and solar panels. Thallium, by contrast, is toxic and used more cautiously, historically in rodenticides and currently in specialized electronics. At the bottom of the group is nihonium, a synthetic element created in particle accelerators. It is highly unstable and exists only briefly in laboratory settings. Its chemical properties are still being explored, but its place in Group 13 suggests it would share some traits with thallium and indium, though with less practical application due to its fleeting nature. Group 13 offers a unique window into the shifting behaviors of elements as atomic number increases, from the complex, non-metallic chemistry of boron to the soft, reactive nature of thallium. This group illustrates how electron configuration guides not only bonding but also physical traits. The boron group is a quiet example of how periodic structure translates into real material diversity, from the hardness of boron to the flexibility of aluminum foil. Now we move into Group 14 of the periodic table, often referred to as the carbon group. This group contains elements that have shaped the foundation of chemistry, biology, and industry. Group 14 consists of carbon, silicon, germanium, tin, lead, and the synthetic element fluorovium. All these elements share a common feature for electrons in their outermost shell. This half-filled valence shell allows for remarkable flexibility in bonding. These elements can gain, lose, or share electrons depending on the conditions, making them highly adaptable. This adaptability gives rise to complex chemistry and, in the case of carbon, the chemistry of life itself. Carbon sits at the top of the group and is exceptional in every way. It forms the backbone of organic chemistry and is the key structural element in all known life forms. Carbon atoms can bond with each other in long chains and complex rings, creating proteins, nucleic acids, carbohydrates, and fats. Its ability to form stable covalent bonds with a wide range of other elements makes it uniquely suited for building large, stable molecules. Carbon can also exist in multiple pure forms, called allotropes, including graphite, diamond, and graphene. Each has different properties, from hardness to electrical conductivity, and all are useful in science and technology. Silicon follows carbon and shares some of its versatility. It is the second most abundant element in the Earth's crust and is widely used in construction and electronics. Silicon dioxide forms the basis of glass, sand, and many minerals. In its purified form, silicon is the cornerstone of modern electronics, used in computer chips and solar panels. Like carbon, silicon can form complex networks of covalent bonds, although its flexibility is slightly more limited. Germanium, tin, and lead continue the trend of increasing metallic character. Germanium is a semiconductor and was used in early transistors before silicon became dominant. Tin is familiar in its use for coating other metals to prevent corrosion and in making bronze when combined with copper. Lead, once common in paints and pipes, is now more carefully regulated due to its toxicity, but it still finds use in batteries and radiation shielding. As we move down the group, the elements become heavier, more metallic, and less chemically active. Fluorovium, the final element in the group, is synthetic and highly unstable. It exists only for fractions of a second in laboratories and has no practical use at this time. Still, its inclusion in Group 14 suggests it shares some chemical tendencies with its group relatives, even if they can only be studied theoretically. Group 14 shows how a single electron arrangement for valence electrons can give rise to vastly different properties. From carbon's role in living systems to silicon's place in global technology, these elements form a bridge between biology, chemistry, and materials science. Now we turn to Group 15 of the periodic table, also known as the nitrogen group. This family of elements reflects a unique balance between gases and solids, between light and heavy, and between biological necessity and industrial use. Group 15 includes nitrogen, phosphorus, arsenic, antimony, bismuth, and the synthetic element, moscovium. All of these elements possess 5 valence electrons, just 3 short of a full outer shell. This configuration gives them the potential to form 3 covalent bonds, and in many cases, they do. The chemistry of this group is rich and diverse, with a gradual shift from non-metallic behavior at the top to metallic properties near the bottom. Nitrogen is the first and most abundant of the group. It makes up about 78% of Earth's atmosphere and is essential to life. Nitrogen atoms form triple bonds in molecular nitrogen, making the gas remarkably stable and inert under most conditions. However, when nitrogen is fixed into usable compounds like ammonia or nitrates, it becomes a crucial nutrient for plants and a foundational element of amino acids and nucleic acids. Its ability to form multiple oxidation states and reactive compounds also makes it valuable in the production of fertilizers, explosives, and synthetic materials. Phosphorus, just below nitrogen, is another key biological element. It is found in DNA, ATP, and phospholipids, which form the membranes of cells. Unlike nitrogen, phosphorus is a solid at room temperature and more reactive. It exists in several allotropes, including white, red, and black phosphorus, each with different properties and levels of stability. Phosphorus compounds are widely used in agriculture and industry, particularly in fertilizers and cleaning products. Arsenic marks the beginning of the metalloids in the group. It has properties of both metals and nonmetals, and has long been known for its toxicity. Despite its dangers, arsenic has uses in semiconductors and specialized glass. Antimony follows, with more pronounced metallic behavior, and is used in flame retardants, batteries, and alloys. Bismuth is one of the heaviest stable elements. It has a low toxicity compared to its neighbors and is often used in cosmetics, pharmaceuticals, and as a substitute for lead in certain applications. Moscovium, the final element in the group, is synthetic and extremely unstable. Its existence is confirmed through a few atoms created in laboratories, and its chemical properties are not fully known. However, its placement in group 15 suggests it may share some of the group's valence behavior, even if only briefly before decaying. The nitrogen group is an example of how a single electron pattern, 5 valence electrons, can support a wide range of behaviors, from atmospheric gases to solid conductors, from life-sustaining compounds to industrial materials. These elements play roles both visible and hidden in the systems we depend on. Now we focus on group 16 of the periodic table, known as the oxygen group or the chalcogens. These elements play an essential role in sustaining life and driving chemical reactions, especially those involving combustion, respiration, and oxidation. Group 16 includes oxygen, sulfur, selenium, tellurium, polonium, and the synthetic element livermorium. Each of these elements has 6 electrons in its outer shell, with 2 electrons missing from a full shell of 8. These elements tend to gain or share electrons during bonding. Their chemistry is active and diverse, ranging from vital biological functions to explosive chemical processes. Oxygen, the first and most abundant in this group, is the element most closely associated with life. It makes up about 21% of Earth's atmosphere and is essential for cellular respiration in most living organisms. Oxygen atoms tend to form 2 bonds, and their high electronegativity means they strongly attract electrons. In respiration, oxygen accepts electrons during the breakdown of glucose, allowing cells to generate energy. It also forms the basis of water, the most common compound on Earth, by bonding with hydrogen atoms. Beyond biology, oxygen is central to combustion, where it reacts with fuels to release energy in the form of heat and light. Sulfur, just below oxygen, is another reactive nonmetal. It is commonly found in volcanic areas and deep within the Earth's crust. Sulfur forms a wide variety of compounds, especially with metals, and plays a crucial role in amino acids and proteins. It also appears in industrial processes, such as the production of sulfuric acid, one of the most widely used chemicals in manufacturing. Sulfur has several solid allotropes, typically forming bright yellow crystals. Selenium and tellurium are metalloids, exhibiting properties between metals and nonmetals. Selenium is used in photocells and electronics, and in small amounts it is essential for human health. Tellurium is less common but valuable in metallurgy and solar panel technology. Both elements continue the trend of decreasing electronegativity and increasing metallic character as we move down the group. Polonium is a radioactive metal discovered by Marie Curie. It is rare and dangerous to handle, but it has specialized uses in devices that eliminate static charges and in certain types of scientific equipment. The last member, livermorium, is synthetic and extremely unstable. Only a few atoms have ever been observed, and its chemical behavior is mostly theoretical. Group 16 reflects a powerful progression. At the top are lightweight, highly electronegative elements that drive respiration and combustion. As we move downward, elements become denser, less reactive, and more metallic. Yet all share the same valence configuration, offering a consistent thread through their varied properties. Now we arrive at group 17 of the periodic table, known as the halogens. These elements are among the most reactive nonmetals, each with a strong tendency to form compounds by pulling in just one more electron. Group 17 includes fluorine, chlorine, bromine, iodine, astatine, and the synthetic element, tennessine. Each halogen has 7 electrons in its outermost shell, just 1 electron short of a full octet. These elements are naturally eager to gain an electron through bonding. This characteristic makes them highly reactive, especially with metals, and explains their frequent presence in both natural and industrial compounds. Fluorine, at the top of the group, is the most electronegative element known. It attracts electrons with incredible strength and reacts with nearly every other element, often violently. It is used in toothpaste as fluoride and plays a role in the manufacture of certain plastics. Despite its aggression as a pure element, in compound form it is stable and extremely useful. Chlorine is perhaps the most familiar halogen, widely used as a disinfectant in water treatment and swimming pools. It is a greenish-yellow gas at room temperature and has a sharp, penetrating odor. Chlorine forms many compounds, including common table salt, where it combines with sodium. It is also used in cleaning products, medicines, and chemical manufacturing. Bromine is unique among the halogens, as it is a liquid at room temperature. It is reddish-brown, volatile, and corrosive. Bromine is used in flame retardants, photographic chemicals, and certain types of medicine. Its reactivity remains high, although slightly less than that of chlorine. Iodine is a dark, lustrous solid that sublimates into a purple vapor when heated. It plays a crucial role in human health, especially in thyroid function. Iodine deficiency can lead to medical conditions such as goiter, which is why it is added to table salt. Though less reactive than the halogens above it, iodine still readily forms compounds and acts as an effective antiseptic. Astatine is a rare and radioactive halogen. It is found only in trace amounts in nature and has no significant commercial applications. Its behavior is not well understood, but it is assumed to follow the trends of the group with increased metallic character. Tennessine, the synthetic member of Group 17, exists only in laboratory conditions and decays almost immediately. Its chemical properties remain largely theoretical. Halogens react vigorously with alkali and alkaline earth metals to form ionic compounds known as salts. Their tendency to gain one electron allows them to form strong, stable bonds. In nature, halogens are rarely found in pure form because they are so reactive. Group 17 illustrates the power of near completion. With only one electron missing from a full outer shell, halogens exhibit sharp, sometimes aggressive behavior that creates some of the most useful and widespread compounds in the chemical world. Now we explore Group 18 of the periodic table, known as the noble gases. These elements are often described as inert, stable, and complete, and they hold a special place in the architecture of atomic behavior. Group 18 includes helium, neon, argon, krypton, xenon, and radon. Each of these elements has a full outer shell of electrons. For helium, that means 2. For the others, 8. This full valence shell makes them exceptionally stable, meaning they do not easily gain or lose electrons. As a result, noble gases do not readily form chemical bonds and are generally found in nature as single, isolated atoms. This non-reactivity is what earned them the name noble, reflecting a kind of independence from the usual chemistry of bonding and exchange. Helium, the lightest of the noble gases, has many uses. It is non-flammable, which makes it ideal for filling balloons and airships. It is also used in cryogenics and scientific equipment because it remains liquid at extremely low temperatures, despite being the second most abundant element in the universe. Helium is rare on Earth and must be extracted from natural gas deposits. Neon is best known for its application in neon signs. When electricity passes through a tube filled with neon gas, it produces a bright red-orange glow. Neon is also used in high-voltage indicators and vacuum tubes. Like helium, it does not form compounds easily and is found only in its pure form. Argon is the third most abundant gas in Earth's atmosphere and is often used to create inert environments in laboratories and industrial processes. It prevents oxidation during metal fabrication and is used in light bulbs to protect the filament. Argon is heavier than air and completely non-toxic, which makes it easy to work with. Krypton and xenon are heavier, noble gases used in specialized lighting, photography, and medicine. Xenon, in particular, has applications in anesthesia and in ion propulsion systems for spacecraft. Both can form compounds under very specific and controlled conditions. But these compounds are rare and typically require high energy or pressure. Radon is a radioactive noble gas produced naturally from the decay of uranium. It is colorless and odorless, and though it is chemically inert, its radioactivity makes it a health concern in enclosed environments. Prolonged exposure to high levels of radon gas can increase the risk of lung cancer, which is why it is carefully monitored in homes and buildings in certain regions. The noble gases serve as a model for atomic stability. Their reluctance to bond makes them chemically quiet, but their presence is anything but trivial. They are used in lighting, medicine, science, and even space exploration. Group 18 teaches us that completeness often brings calm, and in a chart filled with reactive and dynamic elements, these noble companions stand still and balanced. Now we move into the central block of the periodic table known as the transition metals. These elements, found in groups 3 through 12, form the wide middle section of the table and bring with them a remarkable variety of properties and behaviors. Transition metals include familiar elements such as iron, copper, nickel, silver, gold, and platinum, as well as others like titanium, chromium, manganese, cobalt, and zinc. What links them all is a similar electron configuration, particularly involving their d orbitals. As electrons fill these d orbitals, the atoms gain more complex structures, which in turn lead to their varied and often useful characteristics. Unlike the main group elements, transition metals can exhibit multiple oxidation states. This means they can lose different numbers of electrons depending on the chemical reaction. Iron, for example, can exist as Fa² or Fa³, each form participating in different chemical behaviors. This flexibility makes transition metals incredibly versatile in bonding and reactivity. It also gives rise to a range of colors in their compounds, which is why they are often used in pigments, dyes, and stained glass. Transition metals are generally hard, dense, and possess high melting and boiling points. They conduct heat and electricity well, making them essential in wiring, engines, tools, and infrastructure. Their surfaces are shiny and metallic, and many are resistant to corrosion, especially when alloyed with other metals. This is why materials like stainless steel, made from iron and chromium, are so widely used. Catalysis is another field where transition metals excel. Many of them can speed up chemical reactions without being consumed in the process. Platinum and palladium, for instance, are used in catalytic converters in vehicles to reduce harmful emissions. Vanadium is used in the production of sulfuric acid. Even in biological systems, transition metals are key. Iron is central to hemoglobin, which transports oxygen in the blood. Copper helps enzymes function properly. Zinc plays a role in immune function and cell repair. One of the defining features of transition metals is their ability to form complex ions. These are structures where the metal atom bonds with surrounding molecules or ions, often in geometric shapes like octahedrons or squares. These complexes are important in both industrial chemistry and medicine. For example, cisplatin, a platinum-based complex, is used in cancer treatment. Despite their diversity, transition metals share a common thread of adaptability. Their electrons allow them to engage in a range of chemical processes, making them central to both natural and technological systems. From ancient tools to modern electronics, from biological reactions to skyscrapers, transition metals have always been part of how humans shape and understand the material world. Now we take a closer look at three of the most essential transition metals: iron, copper, and zinc. These elements are not only abundant but deeply integrated into both the natural world and human civilization. They are practical, durable, and biologically significant, making them true workhorses of the periodic table. Iron is perhaps the most iconic of the three. It is the fourth most abundant element in Earth's crust and has been used by humans for thousands of years. Its strength, availability, and ease of processing made it the foundation of the Iron Age and the backbone of modern infrastructure. In its pure form, iron is strong and malleable, but when combined with carbon and other elements, it forms steel, a material that supports buildings, bridges, tools, and machinery. Chemically, iron is notable for its ability to exist in multiple oxidation states, most commonly as Fa² and Fa³. This versatility allows it to participate in a wide range of reactions, including those in living organisms. In the human body, iron plays a central role in the transport of oxygen. It is the core component of hemoglobin, the protein in red blood cells that carries oxygen from the lungs to the tissues. Without iron, the body cannot produce enough healthy red blood cells, leading to fatigue and weakness. The body regulates iron carefully, recycling it from old cells and storing excess in specialized proteins. Copper is another essential transition metal, known since antiquity. Copper is highly conductive, second only to silver, and is widely used in electrical wiring, motors, and electronic devices. Its reddish color and resistance to corrosion also make it a common material for coins, pipes, and decorative items. In chemistry, copper can switch between Cu and Cu² oxidation states, giving it a range of reactivity and the ability to form colorful compounds. Biologically, copper is required in trace amounts. It acts as a cofactor in enzymes that manage energy production, iron metabolism, and nervous system function. Deficiencies in copper can lead to developmental issues and impaired immune response, while excess can be toxic. Zinc rounds out this group as one of the most functionally diverse metals in the body. though not as visually striking or historically celebrated as iron or copper, zinc is involved in hundreds of enzymatic reactions. It plays a key role in DNA synthesis, wound healing, immune response, and cellular growth. Zinc is also used in metal alloys, galvanization to prevent rusting, and in everyday products like batteries, sunscreens, and ointments. These three metals bridge the worlds of industry and biology. They are mined, shaped, and alloyed, but also absorbed, transported, and regulated within the body. Their ability to change oxidation states, form complex ions, and participate in both structural and metabolic processes makes them some of the most indispensable elements on the periodic table. Now we turn to three of the most admired and valuable metals in the periodic table: gold, silver, and platinum. These elements are often associated with beauty and wealth, but their true importance lies in their unique physical and chemical properties that have made them essential in both culture and technology. Gold is element number 79 and has been prized since ancient times. Its luster, softness, and resistance to tarnish make it ideal for crafting jewelry, coins, and ceremonial objects. What makes gold chemically special is its extraordinary stability. It does not easily corrode, oxidize, or react with air or water. This resistance to chemical change is a key reason gold has endured as a symbol of purity and permanence across human history. In its pure form, gold is soft and malleable, able to be shaped into extremely thin sheets known as gold leaf. While most people think of gold as decorative, it also plays a crucial role in electronics. Because gold is an excellent conductor and does not corrode, it is used in connectors, switches, and precision components in computers and spacecraft. Silver, element 47, is another noble metal known for its brightness and high reflectivity. It has the highest electrical and thermal conductivity of any element. Because of this, silver is widely used in electronic circuits, solar panels, and batteries. Like gold, silver resists oxidation in dry air, but it can tarnish when exposed to sulfur compounds. In addition to its industrial uses, silver has antimicrobial properties. For centuries, it has been used in medical instruments, dressings, and water purification. In photography, silver halides were once the foundation of film development, though their use has declined in the digital age. Silver's value lies not just in its beauty, but in its adaptability across many fields. Platinum, element 78, is rarer than gold and silver and possesses its own set of remarkable traits. It is dense, heavy, and highly resistant to heat and corrosion. Platinum is widely used in catalytic converters, devices in cars that help reduce harmful emissions. It serves as a catalyst in many chemical reactions, including those used in refining petroleum and manufacturing fertilizers. Platinum also plays a role in medical treatments, especially in chemotherapy drugs. Its ability to form stable complexes makes it effective in targeting and disrupting cancer cells. In jewelry, platinum is prized for its strength and permanence, often used in wedding bands and luxury watches. Together, gold, silver, and platinum are called noble metals not only because of their resistance to corrosion, but also because they occupy a special place in human culture. Their rarity and stability give them lasting value. Their appearance captures the eye, but their true worth lies in what they can do. These elements combine beauty with function, serving purposes far beyond decoration. In industry, medicine, and memory, they are metals that quietly endure. Now we descend into the first of the two rows that sit beneath the main body of the periodic table. This row contains the lanthanides, a group of elements often called the rare earth metals. Though less familiar to most people, these elements are deeply embedded in modern technology and scientific advancement. The lanthanides include 15 elements, beginning with lanthanum and ending with lutetium. They occupy atomic numbers 57 through 71. All share similar chemical properties, primarily because they each add electrons to the same type of orbital. This shared behavior makes them difficult to separate from one another in nature, which is partly why they are called rare. However, they are not especially scarce in the Earth's crust. The term rare refers more to the difficulty of extraction and refinement than to actual abundance. Lanthanides are known for their bright and distinct colors when used in compounds. This optical quality makes them useful in applications such as lasers, fluorescent lighting, and colored glass. Europium, for instance, gives off a strong red glow and is used in television screens and LED displays. Terbium produces a green light and is essential in energy-efficient lighting. These unique luminescent properties are linked to the way electrons transition between energy states, emitting specific wavelengths of light. Most lanthanides are silvery white metals that are soft and can be cut with a knife. They tarnish quickly when exposed to air and react with water slowly to release hydrogen gas. Chemically, they tend to form trivalent ions, meaning they most often carry a 3+ charge when part of a compound. These ions are stable and predictable, which contributes to the lanthanide's usefulness in forming strong, consistent chemical bonds. Lanthanum, the namesake of the series, is often used in camera lenses and battery electrodes. Neodymium is widely recognized for its use in powerful permanent magnets, which are essential in headphones, wind turbines, and electric motors. These magnets combine strength with lightness, helping reduce the size of electronic components. Other lanthanides are used in polishing glass, refining petroleum, and even in nuclear reactors. Despite their similar chemistry, each lanthanide has a specific role in science and industry. Their electron structures allow for fine control of light, magnetism, and energy. In medical imaging, for example, gadolinium is used as a contrast agent in MRI scans because of its magnetic properties and ability to enhance image clarity. The ability of these elements makes them highly valuable in precision work. The lanthanides quietly support the foundations of modern life. Though rarely mentioned in everyday conversation, they are essential to the devices and technologies that define our era. Their brightness is not only literal, but symbolic of the depth and complexity hidden within the periodic table's lower rows. Now we continue into the second row beneath the main body of the periodic table, the actinides. These elements carry a different kind of significance. While the lanthanides are bright and useful, the actinides are powerful, unstable, and often radioactive. They form a bridge between chemistry and nuclear science, between structure and energy. The actinide series begins with actinium and ends with lawrentium, covering atomic numbers 89 through 103. Like the lanthanides, the actinides share a common electron configuration pattern, filling the 5f orbitals. These electrons lie deep within the atom and give rise to complex behavior, particularly in terms of bonding and radioactivity. While all actinides are technically metals, they are not used in the same way as other metallic elements. Many are unstable, and most are not found naturally in significant amounts. Uranium and thorium are the two most naturally abundant actinides. Both are radioactive and have been used as fuel sources for nuclear power. Uranium-235, in particular, is capable of sustaining a nuclear chain reaction, making it central to both civilian energy production and military technology. Thorium has also shown promise as an alternative fuel source due to its abundance and relatively lower radioactive waste. Plutonium is another well-known actinide synthesized during the early 20th century. It is dense, silvery, and extremely radioactive. Like uranium, plutonium can be used in nuclear reactors and weapons. Its role in history is tied to the development of nuclear arms, but it also plays a part in space exploration, where its radioactive decay provides a long-lasting energy source for deep space missions. Beyond these three, the other actinides are mostly synthetic and have very short half-lives. Elements like americium, curium, and berkelium are created in laboratories, often as byproducts of nuclear reactions. Americium is used in small amounts in smoke detectors, where its radioactive emissions help detect particles in the air. However, most synthetic actinides have limited use outside of research and experimental physics. Their instability and high levels of radioactivity make them difficult to handle and store. Chemically, the actinides tend to form a variety of oxidation states, which means they can bond in multiple ways depending on their environment. This adds complexity to their study and use. Their radioactivity also changes how they are handled. Shielding, containment, and time are all factors when dealing with actinide materials. Despite their challenges, actinides have helped humans unlock the secrets of the atom. They reveal how matter transforms, how energy can be harnessed, and how the very building blocks of reality can shift over time. In studying them, we not only uncover the limits of chemical behavior, but also the possibilities of what lies beyond. The actinides remind us that the periodic table is not just a list of elements, it is a map of instability. Now we focus more closely on two of the most significant elements in the actinide series, uranium and plutonium. These elements do more than sit quietly in the bottom row of the periodic table. They represent the immense power stored in atomic matter, a power that has been used for progress and also feared for its potential consequences. Uranium, with atomic number 92, is a heavy, silvery gray metal that occurs naturally in the Earth's crust. It is mildly radioactive, and while it is not rare, its usefulness lies in the unique properties of one particular isotope, uranium-235. This isotope is capable of sustaining a nuclear chain reaction, meaning that when it splits, it releases energy and additional neutrons that can split other nearby uranium atoms. This cycle creates a rapid release of energy, which is the basis for both nuclear power and nuclear weapons. In peaceful applications, uranium is used in nuclear reactors to generate electricity. The controlled fission of uranium-235 heats water, creating steam that turns turbines. This process produces vast amounts of energy with minimal greenhouse gas emissions. Uranium fuel is packed into rods and managed carefully, with cooling systems and containment structures designed for safety. However, even under strict control, the waste it leaves behind remains radioactive for thousands of years, posing long-term storage challenges. Plutonium, atomic number 94, is not found in large quantities in nature. It is mostly produced by bombarding uranium-238 with neutrons in nuclear reactors. Plutonium-239 is the isotope of greatest interest because, like uranium-235, it can sustain a chain reaction. It is denser and more radioactive than uranium and has been used in both power generation and the cores of nuclear weapons. The dual nature of plutonium reflects a deeper tension in its use. On one hand, it offers a concentrated form of energy. On the other, its potential for destruction has made it a symbol of human responsibility. Plutonium-based radioisotope generators have also powered space probes and rovers. These devices convert the heat from plutonium decay into electricity, allowing missions to operate far from the Sun, such as those exploring the outer planets or deep space. Handling both uranium and plutonium requires layers of safety protocols. These metals must be stored in shielded containers, monitored for leaks, and transported with care. Exposure can cause radiation sickness, and contamination must be avoided. Both elements challenge our ability to manage powerful tools wisely. What makes uranium and plutonium so significant is not just their radioactivity, but the role they play in shaping global energy, security, and technology. They embody the dual edge of scientific progress. Harnessed properly, they offer clean energy and deep space exploration. Misused or poorly managed, they carry risks that extend beyond borders and generations. Now we return to the very beginning of the periodic table, to element number 1, hydrogen. Despite its simple structure, hydrogen is far from ordinary. It is the lightest and most abundant element in the universe. It is also one of the most essential, playing a critical role in the chemistry of life, the energy of stars, and the structure of matter itself. Hydrogen is unique because it does not neatly fit into any one group on the periodic table. It is usually placed above the alkali metals in group 1, but its properties are distinct. Unlike metals, hydrogen is a colorless, odorless, and tasteless gas under normal conditions. It consists of just one proton and one electron. There is no neutron in the most common form of hydrogen, making it the simplest atom possible. This simplicity gives hydrogen its flexibility and special status. In the universe, hydrogen is the most plentiful element by far. It fuels the stars, including our Sun. Through a process called nuclear fusion, hydrogen atoms in the Sun's core collide and fuse to form helium, releasing massive amounts of energy in the process. This energy is what gives the Sun its light and heat. On a cosmic scale, hydrogen is the raw material from which galaxies, stars, and planets are formed. On Earth, hydrogen is rarely found in its pure elemental form. Instead, it is usually bonded with other elements. Water, for example, is composed of 2 hydrogen atoms and 1 oxygen atom. Organic molecules, the chemical compounds that make up living organisms, are built on frameworks that include hydrogen. In fact, without hydrogen, life as we know it would not exist. It is found in carbohydrates, proteins, fats, and DNA. It plays a role in the structure of cells and the function of enzymes. Hydrogen is also a key player in energy discussions. It has long been studied as a clean fuel. When hydrogen gas is burned or used in fuel cells, it combines with oxygen to produce water. This reaction releases energy without emitting carbon dioxide or other pollutants. As a result, hydrogen is seen as a possible solution for reducing the environmental impact of transportation and industry. However, producing pure hydrogen still requires energy, and developing sustainable ways to do so remains a major challenge. Chemically, hydrogen can act as both a metal and a non-metal. It can lose its electron to form a positive ion or gain an electron to become negative, depending on its environment. This dual nature allows hydrogen to form a wide range of compounds and take part in many different types of chemical reactions. Hydrogen stands at the threshold of chemistry. It is where the periodic table begins, where stars are born, and where life finds its structure. Though it is small and often overlooked, hydrogen is the thread that runs through the fabric of both matter and energy. Now we come to helium, element number 2 on the periodic table. It sits quietly at the top of group 18, the noble gases, and lives up to its group's name with a remarkable sense of calm. Helium is the second most abundant element in the universe, formed during the earliest stages of the Big Bang and continuously produced in the cores of stars. Though it is small and invisible, its stability and usefulness reach far beyond what most people imagine. Helium is a colorless, odorless, tasteless gas that is completely inert. It does not react with other elements under normal conditions, a trait it shares with the rest of the noble gases. This lack of reactivity is due to its electron configuration. Helium has 2 electrons, which perfectly fill its only shell. With its energy level full, helium has no need to gain, lose, or share electrons. This makes it one of the most stable elements known. In everyday life, helium is most famously used to fill balloons. Because it is lighter than air and non-flammable, it offers a safe way to create lift. Unlike hydrogen, which is also light but highly reactive, helium provides buoyancy without danger. But its uses go much deeper than birthday parties and floating decorations. Helium plays an essential role in science and industry. One of its most valuable properties is its low boiling point. Helium becomes a liquid at just above absolute zero, colder than any other element. This makes it ideal for cooling superconducting magnets, particularly those used in magnetic resonance imaging or MRI machines. In these machines, helium helps maintain the extremely low temperatures needed for the magnets to function without electrical resistance. Helium is also used as a protective gas in welding and in the production of fiber optics and semiconductors. Its inertness prevents unwanted chemical reactions during manufacturing. In deep-sea diving, helium is mixed with oxygen to create a breathing gas that reduces the risk of nitrogen narcosis, a dangerous condition that affects divers at great depths. Despite its abundance in the universe, helium is relatively rare on Earth. It is produced through the natural radioactive decay of elements like uranium and thorium. As helium atoms form, they accumulate in natural gas deposits deep underground. Extracting helium is a complex process, and once released into the atmosphere, it escapes into space, never to return. This means helium is a non-renewable resource on a human timescale, and efforts are being made to conserve and recycle it. Helium may seem quiet and simple, but it is vital in areas where precision, safety, and stability matter most. From medicine to deep space, from tiny atoms to massive stars, helium stands out not by how it reacts, but by how it refuses to. It is a reminder that in a world full of change, sometimes stability is the most powerful quality of all. Now we come to carbon, element number 6, the foundation of all organic chemistry. Carbon is not the most abundant element in the universe, nor the most reactive, nor the heaviest. Yet it plays a role unlike any other. It is the element that builds life. Every cell, every strand of DNA, every protein, fat, sugar, and enzyme relies on carbon's unique ability to form bonds with itself and with many other elements. It is, in every sense, the backbone of life as we know it. Carbon atoms have 4 electrons in their outer shell, which can hold up to 8. This gives carbon a kind of balance. It is not eager to lose all 4 electrons, nor does it readily gain for more. Instead, it prefers to share, forming covalent bonds with up to 4 other atoms. This quality allows carbon to build strong, stable chains, rings, and complex frameworks. These structures can be simple, like methane, or extraordinarily complex, like the molecules that make up hormones or genetic material. The versatility of carbon comes not just from the number of bonds it can form, but also from how those bonds are arranged. Carbon can form single, double, or triple bonds. It can link in straight chains, branched paths, or closed loops. It combined with hydrogen, oxygen, nitrogen, sulfur, and many other elements. This diversity creates a near infinite number of possible compounds. That is why the study of carbon-based compounds is a field of its own, called organic chemistry. In the natural world, carbon takes many forms. It is found in the atmosphere as carbon dioxide, in the earth as coal and graphite, and in our bodies as sugars, amino acids, and fats. Diamonds, one of the hardest known materials, are pure carbon arranged in a tight, repeating lattice. Graphene, a single layer of carbon atoms arranged in a hexagonal grid, is one of the strongest and most conductive materials ever discovered. These physical forms reveal another layer of carbon's richness. Biologically, carbon forms the framework of every major molecule. Carbohydrates provide energy, proteins carry out functions and build structure, lipids form membranes, and nucleic acids store genetic instructions. Each of these depends on carbon's flexible bonding. The cycle of carbon through the environment, moving from the air into plants through photosynthesis, then into animals and back again through respiration and decay, is a key part of the Earth's balance. Even in energy systems, carbon plays a central role. Fossil fuels such as coal, oil, and natural gas are composed primarily of hydrocarbons. Their combustion releases energy and carbon dioxide. Managing this carbon release is at the heart of today's environmental discussions. As we search for sustainable energy, understanding carbon's behavior helps guide those efforts. Now we arrive at nitrogen, element number 7, a quiet but constant presence in the world around us. It makes up about 78% of the air we breathe, yet it passes through our lungs unnoticed. It does not nourish us directly or fuel combustion, but without it, life would unravel. Nitrogen is a vital thread in the fabric of biology, woven into the proteins we build, the enzymes we use, and the genetic code that defines every living thing. Nitrogen atoms have 5 electrons in their outer shell, meaning they seek 3 more to reach stability. This allows nitrogen to form strong covalent bonds, often with hydrogen, oxygen, or carbon. The most familiar form of nitrogen is the diatomic molecule N, 2 nitrogen atoms tightly bound together by a triple bond. This bond is so strong that most organisms cannot break it. This is why, even though nitrogen fills the sky, most living beings cannot use it in that form. To become biologically available, nitrogen must first be converted through a process called nitrogen fixation. Certain bacteria and microorganisms can break apart atmospheric nitrogen and convert it into compounds such as ammonia. Plants then absorb these nitrogen compounds from the soil and use them to form amino acids and nucleotides. Animals eat the plants and in doing so, take in nitrogen that becomes part of their own proteins and DNA. In this way, nitrogen circulates through ecosystems, passed from air to soil to plant to animal and eventually back again. In proteins, nitrogen is found in every amino acid, the building blocks of muscles, enzymes, and tissues. In DNA and RNA, nitrogen forms part of the nitrogenous bases, adenine, thymine, cytosine, and guanine, that store and transmit genetic information. Without nitrogen, there would be no heredity, no repair of cells, no way for organisms to grow or reproduce. Its role is subtle, but essential. Nitrogen compounds are also deeply connected to agriculture. Fertilizers rich in nitrogen help crops grow by supplying nutrients plants need but cannot access directly from the air. However, excess use of nitrogen-based fertilizers can lead to runoff that disrupts ecosystems and pollutes water sources. Managing nitrogen responsibly is a central concern in both farming and environmental science. In industry, nitrogen is used in a variety of forms. As a gas, it creates inert atmospheres for preserving food and protecting sensitive electronics. In liquid form, nitrogen is extremely cold and is used for rapid freezing, cryopreservation, and even in medical treatments to remove damaged tissue. Though we cannot see it or taste it, nitrogen is always there. It shapes the air, supports the soil, and resides within us. It connects the invisible world above with the living world below. In every breath, every cell, every strand of DNA, nitrogen quietly serves its role, holding together the code of life with bonds, both literal and symbolic. Now we breathe in the story of oxygen, element number 8, the element most closely tied to life as we know it. It fills our lungs with every breath and fuels countless processes that sustain us. Oxygen is more than just the air we inhale. It is the key to cellular respiration, the silent combustion within us that powers movement, thought, and renewal. Oxygen makes up about 21% of Earth's atmosphere. In its elemental form, oxygen exists as O, a diatomic molecule composed of 2 oxygen atoms held together by a double bond. This bond is strong but not unbreakable. It allows oxygen to participate in many reactions, especially those that release energy. Combustion is one such reaction. When a fuel combines with oxygen, the result is often heat, light, and new compounds such as carbon dioxide or water. This process is visible in fire and invisible in the cells of your body. Within the mitochondria of each cell, oxygen serves a quiet purpose. As nutrients are broken down into smaller molecules, the electrons from these reactions are passed along a chain of proteins. At the end of this chain, oxygen waits to accept those electrons and combine with protons to form water. This final step allows the cell to release energy in the form of ATP, the currency of life. Without oxygen, this entire process comes to a halt, and cells quickly begin to suffer. The air we breathe is not just for lungs. It is for every cell in the body. Oxygen is carried through the bloodstream, bound to hemoglobin in red blood cells. This partnership allows oxygen to travel from the lungs to the tissues and return carbon dioxide back to the lungs to be exhaled. Every heartbeat supports this exchange. Every breath continues the cycle. Oxygen also shapes Earth's landscape and history. It did not always exist in abundance. Billions of years ago, early photosynthetic organisms began releasing oxygen as a byproduct. Over time, this oxygen transformed the atmosphere and allowed more complex life to evolve. It also reacted with minerals in rocks and oceans, changing their composition. The presence of oxygen today is both a gift and a legacy of these ancient microbes. Though essential, oxygen can be dangerous in excess. It is a reactive element and can form compounds known as free radicals, which damage cells if not carefully controlled. Our bodies have evolved antioxidants to manage this balance, but oxygen remains a force that must be respected. Oxygen is also present in countless compounds beyond water. It helps form acids, alcohols, and oxides. It plays roles in combustion engines, water treatment, steelmaking, and medical therapy. In every role, its reactive nature is both its strength and responsibility. To understand oxygen is to understand life's spark. It flows through ecosystems, through veins, through the breath that joins the internal with the external. Invisible but essential, it is the element of energy, of motion, of quiet fire within. Now we explore 2 elements that lie quietly within the body and the earth, yet play crucial roles in biology and industry. Phosphorus and sulfur, elements 15 and 16. are close neighbors on the periodic table, and both carry deep connections to energy, structure, and transformation. Their names echo ancient times when fire and earth were seen as living forces. And in many ways, these elements still carry that spirit. Phosphorus was first discovered in the 17th century by an alchemist distilling urine, revealing a substance that glowed faintly in the dark. The name phosphorus means bringer of light, and this name suits its fiery personality. Pure phosphorus is so reactive that it must be stored underwater to keep it from igniting in air. Yet inside the body, phosphorus is controlled, stable, and indispensable. Every cell in the body relies on phosphorus to store and transfer energy. It is a central part of ATP, the molecule that cells use to move energy from one place to another. Without ATP, muscles would not contract, nerves would not fire, and cells would not build or repair themselves. The phosphate group, containing one phosphorus atom and 4 oxygen atoms, is the key to this process. These groups also form part of DNA and RNA, linking the sugar molecules in the long chains that store genetic information. Phosphorus is also found in bones and teeth, making up a significant portion of their mineral content. In agriculture, it is a core ingredient in fertilizers, where it supports root growth and flower production. Plants absorb phosphorus from the soil in the form of phosphate, and animals in turn receive it by eating those plants. This cycle connects soil, plant, and animal in a quiet rhythm of nourishment. Next to phosphorus on the table is sulfur, an element known since antiquity. Sulfur has a yellow, earthy appearance and a distinct smell when burned, often associated with volcanoes or hot springs. In its natural state, sulfur is stable, but it becomes reactive when heated or combined with other elements. It has been used in gunpowder, medicine, and the vulcanization of rubber. Inside the body, sulfur is part of several amino acids. These sulfur-containing amino acids help shape proteins by forming disulfide bonds, small bridges that stabilize their three-dimensional structures. This gives proteins the ability to fold, bend, and perform their functions with precision. In industry, sulfuric acid is one of the most produced and widely used chemicals, important in refining, manufacturing, and wastewater treatment. Though simple in its structure, sulfur's reactivity and versatility make it valuable in both living systems and engineered processes. Phosphorus and sulfur may not catch the eye like gold or glow like neon, but they light the fires of life in more subtle ways. They store energy, shape proteins, support growth, and keep the delicate balance between reaction and stability. Now we turn our attention to 2 soft, silvery metals that hide in plain sight, quietly conducting the business of life from within. Sodium and potassium, elements 11 and 19, are part of the alkali metal family. They are highly reactive in their pure forms, but in the body they exist as ions dissolved in fluids, creating electrical signals that allow us to move, think, and stay alive. Without them, the very idea of communication between cells would begin to fade. Sodium and potassium each have a single electron in their outer shell, which they easily lose to form positively charged ions. In the natural world, this makes them highly reactive, especially with water, where they fizz and spark. But in living organisms, they are carefully controlled. The body keeps sodium mostly outside the cells and potassium mostly inside. This separation creates a voltage difference across the cell membrane, known as the resting membrane potential. It is this electrical tension that sets the stage for all nerve and muscle activity. Every time you move a finger, blink an eye, or feel a sensation, sodium and potassium ions are at work. Nerve impulses travel down the length of neurons like tiny electrical waves. When a neuron is stimulated, sodium channels open and allow sodium ions to rush into the cell, changing its charge. Immediately after, potassium channels open and potassium flows out, returning the charge to its resting state. This rapid exchange of ions is what produces the signal, allowing messages to travel quickly across the nervous system. The same process drives muscle contractions. From the beating of the heart to the lifting of a hand, these movements depend on the precise balance of sodium and potassium. This is why their levels are so carefully regulated by the kidneys, which filter and reabsorb these ions as needed. Hormones such as aldosterone help fine-tune this process, ensuring that the body maintains a stable internal environment. Sodium also plays a key role in fluid balance. Where sodium goes, water follows. This means sodium helps regulate blood pressure and volume. Too much sodium in the diet can lead to hypertension, while too little can cause fatigue, confusion, or even seizures. Potassium, meanwhile, is vital for heart rhythm, nerve function, and muscle control. A diet rich in fruits and vegetables often provides the potassium needed to balance the sodium from processed foods. In daily life, we encounter sodium as table salt or sodium chloride. It is essential in small amounts, but can become harmful when consumed in excess. Potassium is found in bananas, sweet potatoes, spinach, and beans, supporting countless processes quietly and constantly. Though we rarely think about them, sodium and potassium form a kind of invisible conversation within us. They send signals, trigger movement, maintain rhythm, and hold the balance between rest and action. Now we focus on two elements that bring structure and stability not only to the skeleton, but to the very signals that keep the body alive. Calcium and magnesium, elements 20 and 12, are alkaline earth metals. Though they are often associated with bones and teeth, their roles stretch far beyond the visible. They shape the rhythm of the heart, the contraction of muscles, and the quiet messaging within every cell. Calcium is best known as the mineral that hardens bones and teeth. Nearly 99% of the body's calcium is stored in the skeleton, giving it strength and shape. But that remaining 1%, floating in blood and cellular fluid, is just as critical. Calcium ions serve as messengers inside cells, triggering responses to signals such as hormones and neurotransmitters. When a nerve sends a message or a muscle prepares to contract, calcium is the switch that turns the process on. Muscle contraction relies heavily on calcium. When a signal reaches a muscle cell, calcium is released from storage within the cell. It binds to proteins that allow muscle fibers to slide past one another, creating movement. Once the contraction is complete, calcium is pumped back into storage, ready for the next command. This cycle repeats every time you move, speak, or even breathe. Calcium is also central to blood clotting, helping to form the fibrant mesh that stops bleeding. It plays a part in enzyme function and maintains the electrical activity of the heart. Because these roles are so vital, the body keeps blood calcium levels within a very narrow range. If dietary calcium is low, the body will take it from bones, weakening them over time. This is why a steady intake of calcium through food or supplements is important, especially during growth or aging. Magnesium, while less famous, is no less important. It is involved in over 300 enzymatic reactions in the body. Magnesium helps stabilize the structure of DNA and RNA, supports the production of ATP, and regulates the movement of calcium and potassium across cell membranes. In this way, It keeps nerves firing smoothly and muscles contracting without spasm. Magnesium also supports the health of the heart and blood vessels. It helps regulate blood pressure, supports a steady heartbeat, and can calm overactive nerve signals. A deficiency in magnesium can lead to muscle cramps, fatigue, irregular heartbeat, and even anxiety or mood disturbances. Rich sources of magnesium include leafy greens, nuts, seeds, whole grains, and legumes. Together, calcium and magnesium maintain a delicate balance. They strengthen the body's framework and keep its internal systems running quietly and reliably. They support the tension between structure and flow, stability and movement. Though they often work in the background, their presence is deeply felt in every heartbeat, every step, and every breath. They are the steady hands that hold the rhythm of life in place. Now we meet to halogens, with sharp personalities and essential purposes. Fluorine and chlorine, elements 9 and 17, are among the most reactive elements on the periodic table. Their nature is to seek one more electron to complete their outer shell, and in doing so, they form powerful bonds and play protective roles in both biology and industry. Though they are small in size, their impact is deep and wide. Fluorine is the most electronegative element, meaning it has the strongest pull on electrons. In its pure form, fluorine is a pale yellow gas that is dangerously reactive. Yet when controlled, its compounds are surprisingly useful and even beneficial. In the body, fluoride is found in teeth and bones, where it helps to harden and protect them. It replaces the hydroxyl group in tooth enamel with a stronger fluoropatite structure, making teeth more resistant to acid produced by bacteria. This is why fluoride is added in small amounts to toothpaste and sometimes drinking water. Its protective quality is subtle, but it helps reduce tooth decay and maintain dental health over time. Beyond dentistry, fluorine is used in the production of pharmaceuticals, refrigerants, and specialized materials such as Teflon. Because of its high reactivity, it must always be handled carefully. Even in industrial settings, fluorine is never used in its elemental form, but rather as part of stable compounds that can be directed with precision. Chlorine is more familiar to most people. It is used to purify water, bleach fabrics, and manufacture a wide range of chemicals. In its elemental form, chlorine is a greenish-yellow gas with a sharp, acrid smell. It is highly toxic and was even used as a weapon in the First World War. But when bonded with sodium, it forms ordinary table salt, a compound so essential that it has been traded and valued for centuries. Inside the body, chlorine exists mainly as the chloride ion. It is one of the most abundant electrolytes in the body and works alongside sodium and potassium to regulate fluid balance, blood pressure, and nerve function. Chloride also helps maintain the acidity of the stomach, forming hydrochloric acid, which breaks down food and kills harmful bacteria. Without chloride, digestion would stall and absorption of nutrients would be impaired. Despite their reactivity, both fluorine and chlorine serve as protectors. They defend against tooth decay, purifying water, support digestion, and help balance the body's internal environment. Their strength lies not in brute force, but in controlled reactions that preserve health and prevent harm. In their natural forms, these halogens are too aggressive for life to handle. But shaped by chemistry and guided by biology, they become guardians of function and stability. They remind us that even the most reactive forces, when tamed and balanced, can become vital parts of a peaceful and well-functioning world. Now we turn to two quieter members of the halogen family, iodine and bromine. Though less reactive than their siblings, fluorine and chlorine. they still carry the halogen signature of forming strong bonds and playing essential roles in living systems and the environment. Both iodine and bromine act in the shadows, working inside tissues, glands, and even the oceans, where their presence helps maintain balance, protect health, and support biological rhythms. Iodine is most well known for its vital role in the endocrine system. It is an essential component of the thyroid hormones produced by the thyroid gland, located in the front of the neck. These hormones, called T3 and T4, regulate metabolism, control body temperature, support brain development, and influence heart rate and energy levels. Without enough iodine, the thyroid cannot produce sufficient hormones, leading to conditions such as goiter, fatigue, or developmental delays in children. The body does not store large amounts of iodine, so a steady intake is necessary. Iodine is naturally found in seafood, seaweed, dairy, and eggs. In many parts of the world, table salt is iodized to prevent deficiency. This public health measure has dramatically reduced cases of goiter and cognitive impairment caused by low iodine levels. Beyond the thyroid, iodine has antiseptic qualities. It is often used in hospitals and clinics as a disinfectant to clean wounds and prepare skin for surgery. Iodine-based solutions can kill bacteria and fungi, making them valuable tools in preventing infection. Bromine, element 35, is less familiar but still important. It is the only non-metallic element that is liquid at room temperature, with a reddish-brown color and a heavy, distinct smell. Bromine is used in flame retardants, certain medications, and some agricultural chemicals. In water treatment, bromine compounds can be used to disinfect pools and hot tubs, offering an alternative to chlorine. In the natural world, bromine plays subtle but significant roles. In marine environments, bromine compounds help regulate ozone levels and participate in complex atmospheric reactions. Certain marine organisms, such as algae and sponges, use bromine-containing compounds as defense mechanisms, signaling the element's importance even in microscopic ecosystems. Together, iodine and bromine show that not all important elements are loud or dominant. Some whisper their effects through hormonal balance, tissue development, or quiet chemical reactions in the sea. Their power lies in precision, not intensity. They support the deeper rhythms of biology and protect against imbalance and disease. In their own subtle ways, they help life stay ordered, responsive, and whole. Now we follow the quiet rhythm of blood as it flows through the body, carrying with it the essential breath of life. At the heart of this journey is iron, element number 26, a metal so central to biology that without it, life as we know it would simply stop. Iron's story is one of motion, of exchange, of carrying the very oxygen that fuels our cells. Iron's most vital role is in hemoglobin, the protein found in red blood cells. Each hemoglobin molecule contains 4 iron atoms, each capable of binding to 1 molecule of oxygen. This bond forms in the lungs, where oxygen levels are high, and breaks in the tissues, where oxygen is needed. This reversible attachment allows hemoglobin to pick up oxygen and release it exactly where it is required. It is a beautifully efficient system, with iron acting as the central hook on which each oxygen molecule briefly rests. This ability to bind and release oxygen is not just useful, it is critical. Every organ, every cell, every tiny process in the body depends on oxygen to produce energy. Without iron, there would be no oxygen transport, and without oxygen, there would be no life. When iron levels are too low, the result is anemia, a condition marked by fatigue, weakness, and pale skin. This happens because the body cannot make enough functional hemoglobin, reducing the blood's ability to carry oxygen. Iron is also a component of myoglobin, a protein in muscle tissue that stores oxygen for use during activity. This is especially important in the heart and skeletal muscles, which require a steady supply of oxygen to keep moving. Beyond oxygen transport, iron supports many enzymes involved in metabolism, DNA synthesis, and cell growth. It even plays a role in the immune system, helping to fight off infections. The body carefully regulates iron levels. Too little iron can lead to anemia, but too much can be toxic, damaging organs and tissues. Iron is absorbed from the diet, particularly from foods like red meat, lentils, spinach, and fortified cereals. The intestines control how much is absorbed based on the body's needs. Unlike many other nutrients, there is no natural way to excrete excess iron, which is why balance is so important. Hemoglobin also gives blood its red color. When iron binds to oxygen, the molecule changes shape slightly and reflects light differently, producing the bright red of oxygen-rich blood. As oxygen is released, the color darkens, giving venous blood its deeper hue. Iron's quiet strength lies in its constancy. It does not command attention, yet it makes every breath meaningful. It supports energy, resilience, and movement from within. By carrying oxygen through the bloodstream, iron links the air we breathe to the life we live, every second of every day. Now we arrive at zinc, element number 30, a quiet regulator that moves through the body with subtle precision. Unlike elements that spark reactions or build structures, zinc shapes what happens behind the scenes. It does not carry oxygen or form strong bones, yet its influence touches nearly every cell, guiding enzymes, supporting immunity, and helping the body respond to its environment with clarity and control. Zinc is classified as a trace element, meaning the body needs it in small amounts. But within those narrow limits, its impact is vast. More than 300 enzymes depend on zinc for their function. These enzymes are responsible for processes as varied as digestion, nerve transmission, cell division, and DNA repair. Without zinc, many of these activities would slow down or stop entirely, leaving the body less able to grow, defend itself, or heal. One of zinc's most important roles is in the structure of enzymes. It stabilizes the shape of proteins, especially in areas known as zinc fingers, where the element helps form loops that allow proteins to bind to DNA. These zinc finger proteins help regulate gene expression, turning certain genes on or off depending on the body's needs. This makes zinc not just a helper of reactions, but a guide in the body's decisions about what to build, repair, or ignore. Zinc also plays a central role in the immune system. It helps produce and activate certain white blood cells, and it supports the communication between immune cells during times of stress or infection. A deficiency in zinc can lead to increased vulnerability to colds, delayed wound healing, and even a loss of taste or smell. These sensory losses occur because zinc is also needed for the maintenance of sensory neurons and epithelial tissue. In addition to immunity, zinc supports growth and development, particularly during periods of rapid change such as childhood, adolescence, or pregnancy. It contributes to the health of skin, hair, and nails, and plays a role in hormone production, including insulin and reproductive hormones. It is found in foods such as meat, shellfish, legumes, nuts, and seeds. And though deficiency is rare in balanced diets, it remains a concern in areas with limited food variety. Unlike iron, zinc does not travel in the blood attached to large proteins. Instead, it moves in and out of cells with the help of specialized transporters that ensure it reaches the places where it is needed most. These pathways are still being studied, and scientists continue to uncover new ways in which zinc influences health and disease. Zinc is quiet but essential, a fine-tuned regulator rather than a bold performer. It brings balance to the molecular stage, allowing reactions to proceed smoothly, systems to adapt, and the body to respond with care. It reminds us that health is not only about force or strength, but about precision and harmony. Now we turn to three lesser-known metals whose roles are often hidden behind the more familiar elements. Cobalt, chromium, and manganese occupy quiet positions in the periodic table, yet their contributions to biology are steady and indispensable. They do not appear in large quantities, nor do they dominate the body's systems, but they support key processes that would falter without their presence. Cobalt, element 27, is central to the structure of vitamin B12, also known as cobalamin. This is the only vitamin that contains a metal ion at its core. The cobalt atom inside B12 allows the vitamin to carry out complex biochemical reactions that support DNA synthesis, red blood cell production, and neurological function. Without enough cobalt, or more specifically, without enough B12, the body can experience anemia, fatigue, and damage to nerves. Since B12 is found mainly in animal products, vegetarians and vegans often supplement it to maintain healthy levels. In addition to its role in B12, cobalt can influence oxygen sensing in cells. Specialized proteins called hypoxia-inducible factors respond to changes in oxygen levels, and cobalt can mimic low oxygen conditions, helping researchers understand how cells adapt to stress. Though cobalt is required in tiny amounts, excessive exposure can be toxic, which is why it is so carefully balanced in living systems. Chromium, element 24, plays a role in the regulation of blood sugar. It enhances the action of insulin, the hormone that allows glucose to enter cells and be used for energy. Though chromium is not part of insulin itself, it supports the hormone interaction with its receptors on cell membranes. Some studies suggest that chromium supplementation may improve glucose control in people with diabetes or insulin resistance. Although results are mixed and ongoing research continues. Chromium is also involved in the metabolism of fats and proteins. It is found in foods such as whole grains, meats, fruits, and vegetables, though the exact amounts vary based on soil content and food processing. Like other trace metals, chromium must be present in the right amount. Both deficiency and excess can disrupt balance, which is why the body tightly regulates its absorption and excretion. Manganese, element 25, is involved in a wide range of enzymatic reactions. It helps form antioxidant enzymes such as superoxide dismutase, which protects cells from oxidative stress. Manganese also supports bone formation, collagen production, and the metabolism of amino acids and carbohydrates. It is present in foods like nuts, seeds, whole grains, and leafy vegetables. These three elements do not work alone. They partner with larger molecules, slipping into enzyme structures or binding to proteins, guiding the flow of energy and information within the body. They do not draw attention to themselves, but they are always active, steady in processes and supporting the systems that keep life moving. Now we focus on silicon, element 14, a bridge between the world of minerals and the age of machines. Though it is often associated with computers and semiconductors, silicon's story begins deep within the Earth, shaped by geological time and elemental fusion. As one of the most abundant elements in the Earth's crust, silicon quietly forms the backbone of both natural structures and modern technology. In nature, silicon is rarely found in its pure form. Instead, it appears as silicon dioxide, better known as quartz, or combined with oxygen and other elements in silicate minerals. These minerals make up much of the planet's rocks, sands, and soils. The glass in windows, the dust on your shoes, the shimmer of a gemstone, and the structure of clay bricks all contain silicon at their core. It is a patient builder layered into the very framework of the world around us. In the body, silicon is present in trace amounts, and although it is not officially classified as an essential nutrient, its importance is gaining recognition. It appears to play a role in the development of bones, skin, and connective tissues. Silicon may support the formation of collagen and contribute to the strength and flexibility of cartilage and tendons. It is found in foods such as whole grains, bananas, and certain vegetables, particularly those with firm structures like green beans and cucumbers. Beyond biology, silicon's true fame lies in its electrical properties. In the mid-20th century, scientists discovered that silicon could be purified and structured in a way that allowed it to act as a semiconductor. This means it can conduct electricity under certain conditions and block it under others. This duality makes silicon ideal for controlling electrical signals, and it became the foundational material for transistors, the small switches that power every computer chip. The result was a revolution. The Silicon Age brought about personal computers, smartphones, satellites, and the interconnected digital world we know today. The name Silicon Valley, the heart of the technology industry, pays tribute to this unassuming element. Without silicon, the language of code would have no voice, and the devices we depend on daily would not exist. Silicon chips are crafted with extraordinary precision, using wafers sliced from crystal cylinders and etched with microscopic circuits. These chips hold and transmit data, enabling calculation, communication, and automation on an unimaginable scale. Yet at the atomic level, they are still governed by the same physical laws that guides elements on the periodic table. Silicon is a reminder that strength can be silent, and that the most transformative forces may rise from the simplest materials. From the sand beneath our feet to the circuits in our hands, silicon connects the ancient with the futuristic. It is the quiet conduit between earth and mind, between structure and signal, between the past and the possibilities of tomorrow. Now we come to aluminum, element 13, a metal known not for its heaviness, but for its lightness and versatility. Found abundantly in the Earth's crust, aluminum is everywhere in aircraft frames, soda cans, kitchen foil, power lines, and even inside the human body. It is a quiet workhorse of the modern world, offering strength without burden, resilience without weight. Aluminum does not occur naturally in its pure form. It is always bound with other elements, most commonly oxygen and silicon, forming minerals such as bauxite. For many centuries, aluminum remained hidden from human use, locked in compounds too stable to easily separate. It was not until the 19th century that scientists learned how to extract it using electricity, unlocking access to a metal that would soon transform engineering and design. One of aluminum's most defining features is its low density. It weighs about 1/3 as much as steel, yet it is remarkably strong, especially when alloyed with small amounts of copper, magnesium, or silicon. This combination of lightness and strength makes it ideal for airplanes, automobiles, and bicycles, where reducing weight increases efficiency. It also resists corrosion naturally, forming a thin layer of aluminum oxide on its surface that protects it from further damage. In construction, aluminum frames, windows, supports buildings, and reflects heat in roofing materials. In packaging, it seals food, protects medicine, and preserves freshness. In electronics, it conducts electricity efficiently, often serving as wiring and components in small devices. Though its presence is often overlooked, aluminum touches almost every part of our lives. Inside the human body, aluminum plays a more ambiguous role. It is not considered essential, and high levels can be toxic. Yet small amounts enter the body regularly through food, water, and air. The kidneys help remove most of it, and in healthy individuals, it rarely accumulates. Scientists continue to study its long-term effects, particularly in relation to neurological health, but within ordinary exposure, it remains largely passive. Aluminum is also used in medicine and healthcare. Certain anticides contain aluminum hydroxide, which helps neutralize stomach acid. Some vaccines use aluminum compounds as adjuvants to boost immune response. These uses are carefully regulated and have long safety records, though they also reflect how this metal, despite being not essential, has been integrated into human biology and care. What makes aluminum remarkable is its quiet adaptability. It bends without breaking, resists rust without constant maintenance, and strengthens structures without weighing them down. It is neither glamorous nor rare, but its presence makes movement, protection, and efficiency possible on both large and small scales. Now we step beyond what the Earth naturally provides and enter the realm of synthetic elements. These are elements not found in significant amounts in nature, but instead created by scientists through precise and powerful methods. Sitting at the edge of the periodic table, they mark the boundary between discovery and invention. They are the result of human curiosity pushing into places nature never reached on its own. Synthetic elements begin at atomic number 93, right after uranium. These elements are not born in stars or found in rocks. They are created in laboratories through nuclear reactions, where atoms are bombarded with particles until their nuclei fuse or change. This process requires immense energy and exact conditions. The resulting atoms are often unstable, lasting only seconds or fractions of a second before decaying into something else. Elements like neptunium, plutonium, americium, and curium were first synthesized during the 20th century, many of them as part of research related to nuclear energy and weaponry. Their creation opened a new chapter in chemistry and physics, proving that the periodic table was not complete but open to expansion. Later discoveries, such as seaborgium, darmstadtium, and tennessini, extended the table further, each new name honoring scientists or places involved in the work. Because these elements are so unstable, their study is challenging. Scientists must detect them indirectly, observing the particles they emit as they decay. Even if they exist for only milliseconds, that fleeting presence is enough to confirm their identity and position on the periodic table. Each new synthetic element pushes our understanding of atomic structure and the forces that hold nuclei together. Though these elements may seem far removed from daily life, they have already influenced technology and medicine. Plutonium, for example, is used as a fuel in nuclear reactors and as a power source in deep space missions. Americium is found in some smoke detectors, where its radioactivity helps sense the presence of smoke particles. These applications show how even the rarest elements can serve practical purposes. The creation of synthetic elements also raises questions about limits. Is there an end to the periodic table? Will we reach a point where atoms simply cannot be made any larger? Some scientists believe that a so-called island of stability exists, a region of heavier elements that might have longer lifespans and unique properties. Research continues in this direction, combining chemistry, physics, and engineering in the search for what lies beyond. Synthetic elements are not just experiments in force. They are expressions of human imagination and precision, built atom by atom in search of knowledge. They remind us that science does not only explore what already exists, but dares to shape what has never been. These elements may vanish quickly, but their discovery leaves a lasting mark. Now we look at how new elements come into being, not through natural formation, but through the deliberate efforts of scientists working at the very edge of possibility. Discovering a new element is not like finding a new planet or unearthing a fossil. It is more like building something never seen before, one atomic particle at a time. The process is slow, complex, and often invisible to the eye, yet it holds the excitement of true exploration. The discovery of a new element typically happens in a laboratory, inside a particle accelerator or nuclear reactor. These machines allow scientists to smash atoms together with immense force, hoping that the atomic nuclei will fuse into something heavier. Most attempts fail. The incoming particles bounce off, or the fused atom splits apart almost instantly. But occasionally, a new nucleus forms, even if it exists for just a moment. These atomic collisions are not random. They are guided by careful predictions based on nuclear physics and existing patterns in the periodic table. Scientists select specific target atoms and projectiles based on the desired outcome. For example, they might shoot calcium nuclei at a heavier element like berkelium. If successful, the collision creates a new element with a higher atomic number. After the collision, researchers look for decay patterns. Every element decays in a unique way, releasing particles and energy in specific steps. By tracking these emissions and their timing, scientists can determine whether a new element was created. These experiments are repeated many times to confirm the results. Often, the new element lives for less than a second, and only a few atoms are ever detected. Once discovery is confirmed, the new element is submitted for review to international scientific bodies like IUPAC, the International Union of Pure and Applied Chemistry. The discoverers are given the honor of proposing a name and symbol. These names often reflect a place, a scientist, or a property of the element. For example, Tennessini honors the state of Tennessee, while Moscovium is named after Moscow. The process from synthesis to official naming can take years. Accuracy, reproducibility, and international agreement all matter. These elements are often added to the periodic table's far right corner, expanding our view of chemical organization and atomic structure. Beyond the discovery itself, these elements help scientists understand how matter behaves under extreme conditions. They test the boundaries of nuclear stability and help refine models of atomic forces. Some researchers hope that stable superheavy elements might one day be created, with properties useful in new technologies. In the end, the search for new elements is more than a scientific pursuit. It is a symbol of curiosity and human effort. From brief flashes of atomic existence, we gather insights that reshape our understanding of matter itself. Now we arrive at the end, though the table itself has no true edge. The periodic table, once a static chart in classrooms, is today a living document, evolving, expanding, and revealing new layers of meaning as science progresses. It is not just a catalogue of elements, but a reflection of human understanding, a map of the matter that makes us and everything around us. Each square on the table represents not just an atom, but a history. There are stories of ancient elements like gold and copper used by early civilizations, and stories of synthetic elements born just years ago in the controlled chaos of particle accelerators. Some elements sustain life, others bend light or carry charge or glow in the dark. Together, they form a kind of universal alphabet, spelling out the structure of everything from stars to skin to silicon chips. What makes the table feel alive is that it responds to new knowledge. As technology improves and experiments deepen, new elements are added, atomic weights are refined, classifications shift as we learn more about behavior, structure, and interaction. The table breathes with discovery. It waits patiently for the next insight, the next heavy nucleus, the next way of seeing the familiar. The layout itself tells a story. Groups and periods aren't just lines and boxes. They show patterns of reactivity, balance, and change. The way elements line up hints at deeper forces inside atoms, where protons, neutrons, and electrons dance in predictable but mysterious rhythms. The table is ordered but not rigid. It reflects the harmony of physical law and the imagination of human inquiry. Even now, some scientists dream of islands of stability, places where superheavy elements might live longer, revealing properties unknown. Others look for entirely new ways of organizing the elements, based not just on atomic number, but on quantum behavior or bonding tendencies. In this way, the periodic table is both an anchor and a horizon. And now, as you rest, remember that the very atoms in your body are part of this great chart. The calcium in your bones, the iron in your blood, the oxygen you breathe, all have their place here. You carry the periodic table with you, always. And tonight, you've come closer to understanding it. So take a breath. Let it all settle in. You've just learned the entire periodic table while you sleep. A quiet achievement, resting on wonder and curiosity. Before you drift off completely, tell us, where in the world are you watching from? Type your country in the comments. If you found this peaceful and interesting, tap the like button so we know. And if you want more journeys like this, through the stars, the brain, or even the history of medicine, subscribe and let your curiosity dream with us. Sleep well, element by element. We'll see you again soon. Good night.